আচ্ছা, আমার একটা কথা আছে, ইউটিউবে যদি
হ্যাঁ
কাউকে
বলো।
রিপ্লাই রিপ্লাই দিতে হয় তাহলে স্যার সেটা কোন অ্যাকাউন্টে দেওয়া হবে? মানে আমি কি আমার অ্যাকাউন্টে দেবো, নাকি কলেজের অ্যাকাউন্টে দেবো, নাকি ইউটিউব যেটা ক্রিয়েট হয়েছে সেটা দিয়ে দেবো?
বুঝলাম না।
কল্লোল স্যার, অ্যাকচুয়ালি আমি বলছি, আমি তো
হ্যাঁ বলো।
ইউটিউবে তো মানে কেউ কেউ যদি কমেন্ট করে, সেটা কি আমি আমার অ্যাকাউন্টে রিপ্লাই দেবো তাকে, নাকি কলেজের অ্যাকাউন্টে দেবো, নাকি আমাদের ডিপার্টমেন্টেরটা দিয়ে দেবো?
সেটা স্যারকে জিজ্ঞেস করো।
এক কাজ করো, ডিপার্টমেন্টেরটা লগ ইন করে রাখো, ওখান থেকে দিয়ে দাও।
আচ্ছা স্যার, আচ্ছা স্যার।
না, ডিপার্টমেন্টে লগ ইন, ওটা কি চাইছো করতে তুমি? সৌম্যজিৎ কি উত্তর দেবে?
মানে স্যার, যদি কাউকে থ্যাংক ইউ জানাতে বা কিছুই জানাতে হয়, মানে কাউকে যদি একটু ওয়েট করতে বলতে হয়, সেক্ষেত্রেও তো সেটা জানাতে হবে কাউকে।
কিভাবে জানাবে সেটা?
সেক্ষেত্রে স্যার আমার অ্যাকাউন্টে কমেন্ট হিসাবে লিখতে পারি, বা অন্য কারোর অ্যাকাউন্টে কমেন্ট হিসাবে লিখতে পারি।
থ্যাংক ইউটা লিখে আমি বুঝতে পারছি না, এটার উদ্দেশ্যটা কি আমি বুঝতে পারছি না।
স্যার ও বলছে যে যদি এই প্রেজেন্টেশনে কেউ কোনো কমেন্ট করে তার রিপ্লাইটা কোন অ্যাকাউন্ট থেকে দেবে, ডিপার্টমেন্টাল দেওয়াই তো বেটার নাকি?
হ্যাঁ সেইটা দেবে, কিন্তু কোশ্চেনটা আমি অ্যাক্সেস করব না, মানে ওই লিখে করতে হবে, সাইলেন্টলি করতে হবে, যাতে প্রেজেন্টেশনটা না ডিস্টার্ব হয়। আমার কথা বোঝা গেল?
না, ওই ইউটিউবে যদি কেউ প্রবলেম ফেস করে সেইগুলো লিখে বলছে, তাহলে সৌম্যজিৎ ডিপার্টমেন্টের অ্যাকাউন্ট থেকে না করলে ওরা বুঝতে পারবে না যে কে করছে আর কি।
তাহলে
মানে
ডিপার্টমেন্টের অ্যাকাউন্ট থেকেই করবে।
হ্যাঁ হ্যাঁ হ্যাঁ, ওটা ডিপার্টমেন্টের অ্যাকাউন্ট থেকে করা ভালো।
কল্লোল, আমাকে কল্লোল একবার আমাকে লিঙ্কটা পাঠিয়ে দিবি, অ্যাকাউন্টটা সুইচ করে নিয়েছি।
হ্যাঁ, হ্যালো।
হ্যাঁ, আমাকে একবার লিঙ্কটা পাঠিয়ে দিবি ইউটিউবে, আমি অ্যাকাউন্টটা সুইচ করেছি তো, পাওয়া যাবে
ওকে
না।
ওকে, আমি হোয়াটসঅ্যাপ করছি।
হুম হুম হুম।
ওকে ওকে, দুটো লিঙ্কই পাঠাচ্ছি। ওকে।
স্যার, কেউ একজন ডক্টর কৃষ্ণেন্দু দত্ত আসছে।
হ্যাঁ, ও আমার পরিচিত এমএনএম এর ছাত্র, ওকে করে দিতে পারো।
আচ্ছা আচ্ছা
একজনকে
স্যার, ঠিক
করলে কি
আছে।
সবাই কি করতে হবে? না না, দরকার নেই,
না না না
সাগর
না।
ঠিকই বলেছে, আমরা এখন কথাবার্তা বলছি তো, লেট হিম ওয়েট।
আচ্ছা 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 স্যার।
15তে তাড়াতাড়ি করে নেওয়া যাবে। হ্যাঁ,
হ্যাঁ
15তে 6টা 15তে সাবসেট করে জয়েন করে নেওয়া যাবে।
হ্যাঁ হ্যাঁ। আর আমাদের প্রিন্সিপাল বা স্পিকাররা তো এখন কেউ আসেনি দেখছি।
না, এখনো কেউ আসেনি।
বিশ্বজিৎকে ফোন করি তাহলে। আচ্ছা কৃষ্ণেন্দু তো, আচ্ছা ওকে উত্তর দেওয়া যাবে না? প্লিজ ওয়েট আফটার 6:15, এটা দেওয়া যাবে? কৃষ্ণেন্দুকে আফটার 6:15 নেওয়া হবে, এটা জানানো যাবে?
সেটা স্যার আপনি ওকে মেল করে বলতে পারেন।
মেল এখন কোথায় পাবো? এখন মেল তো
হোয়াটসঅ্যাপ বা মেসেজ।
ওনাকে অ্যাকসেপ্ট করা হয়নি?
না না, করা হয়নি।
ওকে ওকে।
স্যার, মেল আইডিটা আমি বলবো, এখানে লেখা আছে।
কার? হ্যাঁ করে
কৃষ্ণেন্দু
দাও
দত্ত।
তাহলে ওনাকে, করে দাও, ম্যাথস ডিপার্টমেন্ট থেকে বলো আপনি চেষ্টা করছেন।
আচ্ছা আচ্ছা আচ্ছা
ওটা করে
আচ্ছা
দাও।
আচ্ছা স্যার।
উই আর অ্যাডমিটিং জাস্ট ফিউ মিনিটস লেটার। ওই দুজনকেই করে দাও।
আচ্ছা কল্লোল, কল্লোল, হ্যালো।
হ্যাঁ স্যার, বলুন।
বলছি একটা স্ট্রিমিং কিন্তু শুরু হয়েছে, আরেকটা লিংক এখনো শুরু হয়নি।
না, আমি করিনি এখনো শুরু।
আচ্ছা, একটা চালু
ওটাই
হয়েছে।
সুবর্ণিত স্যার একটু ওয়েট করতে বললেন, 1 মিনিট। 1 মিনিট কল করছি।
ঠিক আছে।
হুম।
কল্লোল, আমি এখন ইউটিউব চ্যানেল চালাচ্ছি না, যখন প্রোগ্রাম শুরু হবে তখন চালাবো।
হ্যাঁ স্যার, ঠিক আছে।
ঠিক আছে, ওটা ক্লিক করলেই হবে তো নাকি কল্লোল?
হ্যাঁ স্যার, লিঙ্কটা ক্লিক করলেই হয়ে যাবে। আপনি
আমি তো সাবস্ক্রাইব করেছি তো।
হ্যাঁ হ্যাঁ হ্যাঁ, আপনি ওই ভিডিওসে যাবেন, ভিডিওসে গিয়ে দেখবেন একটা লাইভ শো হচ্ছে, সেই লাইভটা ক্লিক করলে হয়ে যাবে।
আচ্ছা, আমি দেখছি তাহলে একটু।
হুম, আপনি খুলে রেখে দিন না হয়, ওটা অসুবিধা নেই চ্যানেলটা।
তনুশ্রী দত্ত, কৃষ্ণেন্দু শ্রী, সাবস্ক্রাইব করবো? ওপরে সাবস্ক্রাইব লেখা আছে।
করে দিন। হুম হুম।
আচ্ছা, ওয়েটিং ফর ম্যাথামেটিক্স ওয়ার্ল্ড, ঠিক আছে। হ্যাঁ বলো। এখন করছে 15-র পরে করবে, নাহলে আমাদের এখন। তাহলে বলে দেবো বলছে। আচ্ছা শোনো, চালু করে দাও।
ওকে স্যার, ওকে স্যার।
9477465329 5329। আমি সবাইকেই বলছি এই নাম্বারে আমাকে কন্ট্যাক্ট করবে, অন্য নাম্বারে করো না।
আচ্ছা স্যার। স্যার একবার
আচ্ছা,
একবার
এবার
বলুন কোন
অ্যাডমিট
নাম্বারটা?
করা শুরু করে দাও সাগর।
ওই
সাগর, অ্যাডমিট করা শুরু করে দাও।
আচ্ছা স্যার, ঠিক আছে স্যার, পড়া শুরু করছি।
হ্যাঁ স্যার, ঠিক আছে,
করো
করছি।
করো। আমাদের স্পিকাররা এলে একটু বলো।
আচ্ছা, লাইভ করে দিয়েছি, ওটা স্ট্রিমিংটা হচ্ছে কিনা একটু চেক করবেন কেউ।
আচ্ছা, না কিশোরও করে দিয়েছে।
ওকে, আমিও চালু
হ্যাঁ
করলাম।
হ্যাঁ হ্যাঁ হ্যাঁ, এটাও দেখা যাচ্ছে।
ওকে ওকে।
আচ্ছা, এটাকে তো সাউন্ডটা মিনিমাইজ করতে হবে।
আপনি সাউন্ডটা অফ করে দিন ওটার।
দিচ্ছি, দাঁড়াও। হ্যাঁ, এটাও দেখা যাচ্ছে। আচ্ছা, এটাকে তো গুড়িয়া গুড়িয়া ও সাউন্ড অফ করে দে।
আচ্ছা, অ্যাডমিট করা শুরু হয়ে গেছে?
হ্যাঁ হ্যাঁ।
ওকে ওকে।
গুড ইভিনিং অতসী।
Good evening.
Sir, Pastopati sir joined us.
হ্যালো, হ্যাঁ প্রেজেন্টেশন বন্ধ করো। হুম হুম হুম। Can you hear me? Can
Yes,
you
we
hear
can.
me?
Yes.
Huh?
Yes, Prashanta, you can be heard. Yes, Prashanta.
Yes, yes.
Thanks a lot. Good evening. I am Dr. Prashantu Shina, Secretary, Organizing Committee, International Webinar on Algebra and Topology. Welcome you all in this today International Symposium on the web. We all are going through a very hard time witnessing the world fighting against COVID-19. Due to this unforeseen outbreak of COVID-19, we all are confined at home and working from home. So we are planning to organize an international symposium on web. Now, I am glad to mention that 626 participants have registered from research institutes, universities, and colleges throughout the country and abroad. It really gives us a pleasure. In today's program, we have our 4 technical sessions. both today and tomorrow, have 2 sessions each. In the first session, we have the speaker, Professor Alan Dow, Department of Mathematics and Statistics, University of North Carolina at Charlotte, USA. A leading topologist will deliver his lecture on compact spaces with a small diagonal. In the second session of today, our speaker is Dr. Vishwajit Vitro, faculty members, Department of Mathematics, University of Bardwan. In the third and fourth session of the second day, a well-known name in the field of category theory, Professor Parthopratim Ghosh, Department of Mathematics and Statistics, University of South Africa, and Professor Muhammad Akbari Tutkaboli, Faculty of Mathematical Sciences, Department of Mathematics, Pure Mathematics rather, University of Gilan, Iran. He is also eminent research. They will deliver their lecture. I have mentioned earlier that 626 people are participating in this August assembly. Only 250 participants have been accommodated in the Google Meet. The rest of the participants are attached to YouTube live stream. For this, I really sorry for not including all in the Google Meet. The viewers of both Google Meet and YouTube live stream are requested to post their relevant questions in the respective chat box. Our team is working on it. I can assure you that your queries will be reached to our respected speakers. In addition, the participants from Google Meet may raise your voice to place the question to the speakers directly after the completion of his speech. Now, I think I'm glad to announce that our respected principal, Dr. Subhrata Kumar Ray, present in the bit. Sir?
স্যার আপনার আনমিউট করুন স্যার।
Yes, yes. Am I audible?
Okay. Once again, I repeat it. Now I am glad to announce that our principal, Dr. Subhrata Kumar Ray, present in the meet. Now I would request our honorable principal to give welcome address and to say something regarding webinar.
Good evening, everybody. Am I audible, Prasantu Babu?
Yeah.
So, good evening, everybody. Today, I think it is a great day for us because we are in a international webinar which is on algebra and topology. So, first, I say something about this topic. Though I know I am not the man of mathematics, but as a subsidiary subject, I have learned it in my BSc level, also in the postgraduate level to some extent. So in mathematics, topology is concerned with the properties of geometric objects that are preserved under continuous deformations such as stretching, twisting, crumpling, and bending, but not tearing or blurring. The topology is the mathematical study of properties that are preserved through deformations, twisting, and stretching of objects. Topology began with the study of curves, surfaces, and other objects in the plane and space. Topology is used in many branches of mathematics such as differential equations, dynamical systems, not theory, and Riemann surfaces in complex analysis. It is also used in string theory in physics and for describing the space-time structure of universe. There is some research in computer science related to computer network that involve topology. This may be divided into physical placement of different components, that is hardware and obligor, the data flows in a particular network, that is the logical topology. In the star network, the best advantage is when there is a failure in cable, then only one computer might get affected, but not the entire network. Star topology is used to ease the probabilities of network failure by connecting all of the systems to a central node. So in this today's international webinar, after this brief introduction of the subject topology, I am welcoming all. I welcome first Professor Alan Dow, University of North Carolina, USA. Sir, on behalf of Prabhu Jagatbandhu College, I heartily welcome you to deliver your speech and enlighten us. Second, I welcome Dr. Biswajit Mitra, University of Burdwan, West Bengal, India. I am inviting you to deliver your lecture. I welcome you to deliver your lecture and enrich us. Again, I welcome Professor Parthopratim Ghosh from University of South Africa to deliver your lecture. So, sir, I welcome you on behalf of Prabhu Jagatbandhu College, West Bengal, India. Fourth, I welcome Professor Mohammad Akbari Tutkaboni, University of Gulian, Iran. Sir, I welcome you on behalf of Prabhu Jagatbandhu College to deliver your speech and enlighten us, enrich our knowledge base on the subject, topic, algebra and topology. So, not only I welcoming the resource persons, but also I welcome all the professors, all research scholars and students participated and others participated in this program. You know, the present day's topic is very vital for the in our modern life, because of the fact that I though I am not the man of this subject particularly, but I have some interest to understand what is the subject means, what is the topic means, and what is the application of it. So the application part of this subject, of this theme, is very important. We are the common people, though who are not actually the directly actually not the man of this subject, but despite that I am actually very much interested. We are very interested to understand it, and we want to listen and also enrich our knowledge base. With these few words, I welcome all, and I think a great success of this international webinar. Thank you all. Welcome all. Thank you again.
I express my sincere thanks to our revered principal for his nice and lucid lecture. Now, let us move to technical session. In the first session, technical session, we're glad to announce that here Dr. Atoshi Devdar, Head Department of Pure Mathematics, University of Calcutta, an eminent researcher in the field of rings of continuous functions, and popular teacher in the Department of Pure Mathematics, are present here. I request Dr. Debra to chair this session.
Thank you, Dr. Sinha. I accept your invitation. So I'm really very happy that you have invited me here in this international webinar to chair this session. It's my great privilege and honor to chair a session where the speaker is someone like Professor Alan Dow, who is a master in the field of set theoretic topology and a famous name in today's mathematical community. Though he doesn't need any introduction, it's my responsibility to brief the audience with his professional whereabouts. So Professor Alan Dow is presently a professor in the Department of Mathematics at the University of North Carolina at Charlotte, USA. He joined this department in 2000 as departmental chair, and prior to that, he was at York University in Toronto, Canada. He was also the chairman of the department there for a short period. Before coming to his professional career, he graduated from University of Manitoba and held several postdoctoral positions in various universities, like University of Kansas, Vrije Universiteit of Amsterdam, Netherlands, and the University of Toronto, Canada. His research interest lies in set theoretic topology, specializing in the set theoretic methods applied to the study of the countable convergence properties of compact spaces. His earlier research was focused mainly on stone-check compactifications. He is currently on various editorial boards of renowned internationally acclaimed journals such as Topology and its Applications, Archive for Logic, and Algebra Universalis. He is also on organizing committees for various conferences like Spring Topology and Dynamics Conference, Summer Topology Conference, and the annual Amy Rudin Young Researcher Award. So today we are eagerly waiting for his talk. The title of his talk is On Compact Spaces with a Small Diagonal. So now I welcome Professor Alan Dow to deliver his lecture. Thank you.
Well, thank you very much, Professor Debray. A very kind introduction. I should turn on my screen. Okay, my entire screen. And here we go. Can you hear me, first of all?
Yeah, yeah.
Yes,
right.
sir, we can hear you.
Okay. Now, I'm not very experienced at
Yeah.
these webinars. And I want to, okay, here we are. Oh, wait. You can see my screen. Can you still hear me?
Yes, sir. Yes, sir, we can,
Yeah.
we can see
All right.
you, see your slide as well as you. And we
Great.
can hear you, no problem.
Okay, okay. Thank you very much. I'm intimidated at such a large, wonderful, diverse audience. Not accustomed, as I said, to this. I'm accustomed to giving a conference where I stare out at the room and see all the blank faces, many of whom start to fall asleep as I start to talk. So I'm going to question, I thought this topic could be a nice balance between showing some elementary methods as well as showing you some cutting edge research for those that are interested in pursuing such areas of research in set theoretic topology. So just to get started in this talk, I want to make you aware that we will be talking about countable sets, and the symbol omega refers to the first countable ordinal. We'll need to be mentioning the ordinals up to omega 1, and then the cardinality aleph 1. So the ordinal omega 1, the von Neumann definition of ordinals, refers to this omega 1 is the set of all smaller ordinals, the set of all countable ordinals, well ordered. And so as I already said, we're talking about an open problem, a very natural kind of question, whether or not certain compact spaces are. And I want to go through some definitions as I introduce the problem. So whether compact spaces, certain compact spaces are separable. So separable means possessing a countable dense subset. The set is dense if its closure is the whole space, if it meets every non-empty open set. A set is metrizable if there's a compatible distance function on it, inducing the topology. Most people's first exposure to topology is in that vein. And we know from Urizon's famous, wonderful theorem that a compact Hausdorff space with a countable base is a separable metrizable space. And the size of a base means the minimum number of open sets, that every non-empty open set is a union from that base. That's one way to say it. And the subject initiated by Arhangelsky and Juhasz, cardinal invariance in topology, that gets the name the weight, the minimum size of a base. So that's called the weight, W, weight for X, the minimum size of a base. Also, I will want to mention the second axiom of topology. The first axiom of topology is often said to be that you have a countable base for your space. The second axiom is that it's called first countable. Every point has a countable local base. I'll want the analog of separable. I'll want the notion of Lindelof. I just realized I didn't define compact. So a space is compact if every cover by the space by open sets will possess a finite subcover. And the generalization of that to Lindelof, the man's name Lindelof, is that every cover by a space by open sets will have a countable subcover. The origins of this interesting problem I had to Google it to go back to 1937. Not the problem I'm talking about, but this well-known characterization of when a compact space is metrizable. Okay, so the diagonal of a set is the set of all, in the Cartesian product x cross x, the set of all points where the two coordinates are the same. So that's the diagonal. I suppose I could draw that, right? So the diagonal, you have x cross x, and then the diagonal is the set of all points like that. Okay, so the characterization is that a compact space is metrizable if its diagonal is a G delta. A G delta means it is the intersection of countably many open sets. So open neighborhoods of the diagonal, you only need countably many to intersect it down to give you the diagonal. We could call that a very small diagonal. And this gives me the opportunity to remind you that the character of a point is the minimum size of its local base, and the pseudo character of a point is the minimum family of open sets that will intersect down and equal the point. And when you have the advantage of being in a compact space, these two cardinals are the same. We'll need that fact as we proceed. So here's a consequence of being a compact metrizable space and a consequence of having a very small diagonal. And it's this property here. So it's an omega-1 property. You might say one of the characterizations of set theoretic or general topology is the frequent mention of omega-1. So if you can say this just simply, if you have an uncountable subset of the product, x squared, of points that are not on the diagonal, same thing to say that the two coordinates don't equal each other, then you can find an uncountable subset of this set. And the original definition was that the closure of that uncountable set avoids the diagonal. This is easy to deduce from it. But the way we'll use it is in this reformulation that if you look at back in X, you look at the closure of the first coordinates of this uncountable set and the closure of the corresponding second coordinates, that those have disjoint closures. So this is a consequence of having a G delta diagonal. And this is the definition of a small diagonal. So you'd say that a space has a small diagonal, not very small, but small, if it has this property. So we will say that a space X is compact small diagonal. So C for compact, S for small, capital D for diagonal. So that'll be the class we're looking at, and say that X is a compact small diagonal space if this proposition holds, right? Given any uncountable set of pairs, you can find an uncountable subset of that, which I might occasionally refer to as omega 1 separated. So the closures of the are disjoint from the closures of the second coordinates. Okay, so that's the question. Is every CSD space metrizable? And it's such a tough open question that I could say, or is it first countable? Or is it an FMF space? You don't need to know what that means. Or is it anything? Can we say anything? Now, I'll say some things, but there's a lot that we just can't say. If you assume, in addition, that the space is first countable, can you prove that it's metrizable? There's all sorts of wonderful, interesting questions that you could pursue about this very innocent-sounding question. Now, as I was preparing for this talk, I had an idea to search for a picture to use to cover up material as I worked. I changed my mind about that, but I came across this picture and it gave me the inspiration to do what I'm about to do, and that is to show you my bibliography in an unusual way. Now, this will take some time away from the development of the talk, and I no doubt will run out of time. I hope not. I practiced and found, oops, my talk is 3 times too long, cut out half of it, it's still twice too long, cut out another half, and I hope I've got it down that it'll fit in the hour, but we'll see. So I found in a tribute to Mary Ellen Rudin this picture. I was really surprised. So online there's a tribute to her, and somebody chose to use this picture. And there I am. I think this was in 1989 at the Oxford Topology Conference, and there's Mary Ellen Rudin. And you mentioned in my introduction that I'm in committee for the Mary Ellen Rudin Young Research Award. It's an annual award dedicated to her memory. And there she is. And that day it was unexpectedly cold in Oxford, and both Mary Ellen and I bought a sweatshirt. I meant to make the joke that this will take away time from the talk, but no doubt everybody will enjoy this part of the talk much more than they will the rest of the talk. So there's Mary Ellen Rudin. I'm going to use elementary submodels in my talk, and I can refer to her also as somebody who absolutely didn't like them. She thought they should stay out of topology, but I pursued anyway. And then there's our wonderful hero, Shura Arhangelski, also giving a talk, I believe, in Oxford. This was when he was much younger. So I'll certainly need one of his great, and then an improvement of one of his great results by, oh, sorry, no, out of order. This is somebody Gary Gruenhaig, who's made a lot of really good contributions to this topic. This was, I don't know if you've heard or knew that Gary Gruenhaig unfortunately had a terrible car accident, and he's now wheelchair bound. And there, I will need their improvement of that result of Arhangelski. There's Istvan Juhas and his frequent collaborator Zoltan Szent-Miklósi. They have some wonderful results, one of which we'll need. This was at the, I think, 1996 Prague Topology Symposium. And okay, and that's pretty much my bibliography, but I wanted to just show you a few more pictures. I stole most of these pictures from, there's Jerry Vaughan. I stole it from his website. There's Jan van Mil, the two chief editors of Topology and its applications. There's a more aged Shura Arhangelski. And there's one of my PhD students, Roberto from Mexico. And then I wanted to show you a couple of my other PhD students. There's a picture from our North Carolina seminar organized by Jerry Vaughan. Jan van Mil was visiting that week. There's one of my PhD students, Geta Takani from Ethiopia, now based in New York. And there's my favorite PhD student, but she actually didn't graduate because she had 2 children and also moved to New York. That's Shuli. And I noticed somebody in the audience has the same surname, Ganguly. So that was Shuli. Anybody else you want to know here? There's Peter Nikos. There's Oleg Pavlov from Russia. And my final PhD, well, I have one more since then, but he's still going. And there's Doyle Barman. Somebody is also named Barman in our list of listeners, so welcome. There's Roberto again. There's Vladimir Kachuk. And okay, so that's my bibliography, and I probably won't be good at keeping track of time. And now let's get going on the material. So I know you didn't want me to just sit and read. So here we go with some of the properties of compact CSD spaces. So my first proposition is a I won't prove it, but it will need it. A closed, my hands are a little bit shaking, I'm nervous. A closed subset of a CSD space is CSD. So that property is closed hereditary. It's not a continuous image. Well, might be, but we don't know, very much don't know. But we'll need that fact, very simple to prove. And here's a little bit of a little flavor of how we can use the CSD property. There is no converging omega-1 sequence. Now, what's a converging omega-1 in CSD spaces? Well, a sequence, omega-1 sequence, of course, just means that it has cardinality omega-1 and it's indexed by omega-1. So you have X alpha alpha element of omega-1 converging, just means in the co-countable sense. So every neighborhood of the limit point X, every open set containing X contains all but countably many of the X alphas. You might say a tail. So the proof that a CSD space cannot contain a converging omega-1 sequence is very simple. You define your family of pairs or your 2-element sets. We didn't have to have them as pairs. They can be 2-element sets. So you take the family of 2-element sets where your first is X alpha and your second is X. I should point out we don't want any trivial omega-1 sequences. Without loss of generality, X alpha doesn't equal X for every alpha. So there's our uncountable family of pairs, and it's easy to see that this is not omega-1, there's not omega-1 separated. You cannot find an uncountable subset of those pairs where the closure of the first coordinates will contain the unique guy in the second coordinate. Okay, so we mentioned first countable already. We know what it means for space to be first countable, and here's another frequently studied cardinal invariant of a topological space called the tightness, probably introduced by Arhangelski. So the tightness of a space X is a cardinal invariant, but we'll only be dealing with countable tightness. So we say the countable tightness if it satisfies this property. If for every point X in a space and for every set A subset of the space, for every X in A closure, X is in A closure if and only if there is a countable subset, a countable B contained in A so that X is in B closure. So that's what countable tightness means, and it's clear that first countable implies countable tightness. There's a couple of frequently studied properties squeezed in between first countable and countable tightness, Frechet property and the sequential property, but I won't, after I trimmed down my talk, I won't need those. Now here's an interesting conclusion about, I could call this a lemma, fact. If you have a space with countable tightness, so closure of every set is just achievable by closing up all the countable subsets, and if you have an increasing chain of closed sets, F alpha equaling F alpha closure contained in F beta for alpha less than beta less than omega 1. So you have an omega 1 increasing chain of closed subsets of your space, then, now it's very rarely true that you can take when you have uncountable tightness, and if you take this increasing union, the point here is the cofinality of the union exceeds the tightness, then this is closed. So it won't be closed at countable limit steps, and then you have to take the closure, but the entire union will be closed. Think about why that's true. Why is it closed? Well, because of countable tightness. If you take a countable subset of this union, and we'll need us to be aware of this frequently, a countable subset of this union, well, pick a point, pick a point, pick a point. Each point you're picking occurs in one of the F alphas. Every countable subset of omega 1 has an upper bound in omega 1. That's the defining characteristic of omega 1. And therefore you have a sufficiently large beta that your entire countable set is contained in F beta, and so the closure of that countable set is contained in F beta. So that's a couple of facts we need about countable tightness. Now a theme for this talk, and a theme for general research in set theoretic topology, I mean, it's not a huge theme, but it's a well-studied theme. So if you can find that less than or equal aleph 1 sized subsets, I can't look out at the audience to see if anybody needs me to slow down, but I do want to make sure I get through. If less than or equal to aleph 1 size subsets of X have a property, whatever topological property you're interested in, then it's natural to ask, then does X have the property? Well, this depends on the property and on the properties of X. But it's a general studying interesting research questions. So that will underlie some of what we'll be doing. So the first example of that I'm going to mention, and I believe this is an old, I mean, I know it's old, but I believe it's due to Juhas and his earlier collaborator, Anders Heinel, and that's separable. So for any X, well, I won't bother saying for any X, just if less than or equal aleph 1 sized subsets of a space are separable, then the space is separable. Then X is not only separable, there's a notion called hereditarily separable. So not only is it separable, but every subset is separable. So that's our first example of this study. Now, how do we prove this, right? Well, we want to pick the right aleph 1 size subset of X to look at. If X isn't separable, we want to find an aleph 1 size subset that isn't separable. And all we do is you just start picking points. We don't have to be clever. Start picking points. X alpha, alpha less than omega 1, and you're just picking them so that, if possible, if we can, X alpha, when you pick him so that he's not in the closure of the points that you've picked so far. So just pick your points arbitrarily, take the closure. If there's any points of x left over, pick a new point, and just keep doing that. So start picking x alpha not in the closure, if possible. If it's ever not possible, that's because x is separable. And if it's always possible, then it's easy to see that if this doesn't stop, then your choice, your aleph 1 size set, x alpha alpha less than omega 1, is not separable. So if x wasn't separable, you've managed to inductively choose an aleph that wasn't separable. And you can similarly do the same for Lindelof. So example 2, same researchers. If less than or equal aleph 1 size sets are Lindelof, if all of them are Lindelof, then x is, again, hereditarily Lindelof. Hereditarily separable, hereditarily Lindelof. Their connections are an extremely important area of study. And basically the same proof. I'm sure I'm going slower than I thought I might, and so I'll skip the proof of that. But it's basically the same idea. You take an aleph 1, you take an open cover that has no no countable subcover, and you start picking points in the members of the cover, and you witness an aleph 1 size subset that isn't Lindelof. Now, a much more difficult and more important, well, I don't know about more important, but anyway, okay, so here's our first reference to Arhangelsky. So this is due to Arhangelsky. And it says, now we're going to have to assume something about the space X. In the first two examples, we didn't have to. For compact X, tightness is this, we call this reflecting. Tightness reflects. For compact X, if the tightness, let me say, if every aleph 1 size set, if every aleph 1 size set has tightness equal aleph 0, then so does X. Now, we would normally state this in the contrapositive. So if you have a compact space X that does not have countable tightness, then it has an aleph 1 size subset that does not have countable tightness. I won't really give the proof, but here introduces something that Arhangelsky introduced and is very important in further research. So if the tightness of X is not countable, so if it's bigger than aleph 0, then not only can you pick an aleph 1 size set with uncountable tightness, you can pick a very, very special uncountable set. So we'll pick, there exists this sequence, we'll inductively pick this sequence, x alpha alpha less than omega 1, and we'll pick a point X to witness the uncountable tightness. But in a very strong sense, it's called a free sequence. So it has this property. So then we pick that, and we pick it such that for every delta less than omega 1, you look at the points with index less than delta, and you take the closure. That's the closure of the initial segment. And you look at the closure of the final segment, starting at delta and going up, that these have disjoint closures. And this is what's known as an uncountable free sequence. And then where do you get X from? Well, here you're going to need compactness, and you also need a countable compactness to be able to pick this sequence from the hypotheses. Then pick any X, pick X, compactness. We can take these final segments, X alpha, delta less than or equal to alpha, less than omega 1, take that closure. Okay, so what? We'll intersect over all delta. So that's a descending sequence of closed sets in a compact space. That intersection is not empty, and so that's why we can pick that X. the complements of these guys form an open cover, has to have a finite subcover, and therefore contradicts that it's a descending sequence. This X is in the closure of this entire sequence of X alphas, but it's not in the closure. So X is never in the closure of the first half. And so that witnesses that the tightness is uncountable. So that was Archangelski. And moreover, and so this I won't try to prove. This is a beautiful result of Juhas and Schmidt-McCloskey, my fourth reference up there. We can choose, so you can choose choice, but you can refine the choice and choose the X alphas so that not only that they form a free sequence, but they actually converge to X. Converge. Co-countably converge. Omega 1 converge. Now wait a minute. This is connected to our problem of CSD spaces, isn't it? So we know that a CSD space cannot have a converging omega 1 sequence. So we have our first informative piece of information about CSD spaces. Now I'm actually going to include two. So we know that CSD spaces do not have converging omega 1 sequences. So here's two properties that would contradict that. So a CSD space has tightness equal L of 0. Great. That's one important new piece of information about CSD space. They're a strange one. And no points with character, that's the minimum cardinality of a local base, exactly equal to L of 1. So a CSD space can certainly have points of countable character, and as far as we know, but we don't know, to be honest, it could have spaces of character, points of character bigger than L of 1, but you cannot have a point with character exactly equal to L of 1, and because otherwise there exists a converging omega 1 sequence. That's a very easy, it's just easier than Archangelski's free sequence. Otherwise, there exists a converging omega 1 sequence. You just start choosing points, choose them in the intersection of the first Conley many, first alpha many neighborhoods of the point. Here, we'll use that pseudo character equals character. The intersection of those Conley many neighborhoods of the point still doesn't equal the point. So you can keep choosing X alphas just from your point X, and you end up with a converging omega 1 sequence. All right, so we've got some new information about CSD spaces. And going back, so I didn't mention before, but the person who posed this wonderful problem is Czech mathematician Mirek Houšek. So this is Houšek's first theorem about CSD spaces. A CSD space of weight, so the minimum size of a base for the topology, less than or equal to L of 1 is metrizable. So if you're going to find a counterexample, it's going to be big. It's going to have weight bigger than L of 1. Okay. Well, how does this proof go? Here I do want to show you the proof because it's going to start exposing the methods that we'll be generalizing. All right, so what do we know? Well, we know by the corollary I just wrote above, we know that if we assume that X is, so let's let X be a CSD space, and we got to prove that it's with weight of X less than or equal to L of 1. And we're going to prove that the weight is actually countable. Well, what we know, so now we know by the corollary above, we know that we don't actually need that X has countable tightness, but we know that X is first countable. every point has a countable local base. Now, there certainly are first countable spaces that have uncountable weight, compact first countable spaces that have uncountable weight, so we're certainly not done. Now, another common thing to do, very useful, is we can use Tikhonov's theorem, and we can say that we may assume let X be a subset, closed subset of the Tikhonov product of omega as weight at most omega 1. We can have him embedded in 0, 1 to the omega 1. Now, I want to use the fact that the space is first countable and make this observation. For every point in X, we can find a countable ordinal delta X, depending on the individual point, element of omega 1 or less than omega 1, so that when we look at X, X is a function from omega 1 into the unit interval. If we restrict that function to the first delta X many coordinates, we'll call that X sub delta X. And what I want to say is that X restricted to delta X is different than Y restricted to delta X for all distinct Y, for all X not equal to Y in X. This is, you can choose countably many basic open sets. You're only going to use countably many coordinates and get a local base for X. And so once you use up all those countably many coordinates, no other point of X agrees with X on the first, agrees with little x on those first countably many coordinates. So that's one thing we're going to need here. Now, speaking of this notation, we're going to define, so more generally, let's define the projection map. So define, we'll call it PR for projection. Pick any ordinal alpha less than omega 1, and the projection map from the full product. Now, you often take projection maps into a single factor, but we'll project it onto the first alpha many coordinates. So just project this onto, it doesn't matter that it's onto, but just the familiar projection map. It's just defined as above. So the projection of alpha of any point X in the full product is sent to the restricted function X restricted to alpha. All right, so what about this projection map? Well, here's an interesting fact. Well, let me just, it's not a fact yet. So let's assume that for a contradiction that X is not metrizable. So we'll prove by contradiction. So what we'll prove is that then X is not CSD, even though we already assumed it was in order to deduce that X was first countable, but we'll achieve a contradiction. Assume that X is not metrizable. Well, then here's a fun fact. Then the projection map restricted to X is never 1-to-1. Why is that? I won't write anything here, I'll just say. Well, X is a compact space. If you have a projection, if you have a continuous function, I forgot to say, these projection maps are well known to be continuous. If you have a continuous function on a compact space, if that function is 1-to-1, it's a homeomorphism. So if X was, if this projection map restricted to X was 1-to-1, you would have a homeomorphic copy of X sitting inside this countable product of unit intervals, and that would turn it into a metric space. The projection map cannot be 1-to-1 if X isn't metrizable. And that is the core idea of how to pick our omega 1 sequence. So for every alpha less than omega 1, go ahead and say, well, the projection map isn't 1-to-1, so pick X alpha not equal to Y alpha, both in X, of course, so that they have the same projection. X alpha restricted to alpha is exactly the same as Y alpha restricted to alpha. And we're ready for our contradiction. So assume, let me change colors for a little variety. Assume A, we're going to try our best for omega-1 separated. Assume A is a subset of omega-1 that is uncountable, and we'll show that it doesn't work. All right, well, let's look at the family X alpha, alpha element of A. So pick, like we did in Archangelski's proof, pick a point X in the intersection over all delta less than omega-1 of the closure of the points X alpha. Now, make them come out of, so that delta is less than alpha, but alpha should come out of the set A. And take that intersection. So this is the closure. You can think of that closure in the space X. Intersection of a family of, if descending family of closed sets, it's not empty, so we can pick such a point. So there's that point. Okay, we're ready for our contradiction. I hope you're still with me. Well, look at his special countable family of neighborhoods. X restricted to alpha is necessarily in the closure. Now this closure is taking place in 0, 1 to the alpha of this set. The projections down to delta sub X of X sub alpha, and just restrict our attention to delta sub X less than alpha in A. Okay, well that's because the projection map is continuous. X is in the closure of all those X alphas, so the projection of X is in the closure of the projection of all those X alphas. So that's because the projection map is continuous. Now wait a minute, what was special about these X alphas and Y alphas? This is the same as the closure. Well, every one of these guys is exactly the same as every one of these guys. The Y alphas and X alphas have the same projections. They have the same projections down to X 0, 1 to the alpha, which makes it even more true that they have the same projections down to 0, 1 to the delta sub X. Well, now we have a problem, and I'll just leave that as a bit of an exercise. Hence, now if X is in the closure of the projection of this set, then there's some point in the closure of that set that projects down to X, but the only point in X that projects down to our point X is X. So that tells you that X is in Y alpha. You can even say bigger than delta X, but that we don't need now. Right, so look at that uncountable subset, and X has to be in that closure, and it's because of this. It's because there has to be a point in that closure that projects to X, but X is the only point that projects to X because of the first countability. Okay, I'm thinking I might have be sure to maybe give me a warning when it's to the end. I've totally lost track of time. I can see what time it is, but I can't remember what time I started. I want to introduce elementary submodels. So we're going to say that M, a non-empty set, is an ESM. We'll use that abbreviation. And this abbreviates elementary, referring to logic, referring to formulas, elementary submodel. Now, to avoid complications from famous Gödel's incompleteness theorems, you have to be careful about what you mean elementary submodel of what. We don't need to worry about that today. So, but I'm just going to tell you, this is called the Tarski-Vought criteria for when something is an elementary submodel, and it's not at all confusing. Elementary submodels, when you start working with them, are confusing because of their seemingly impossibly powerful, but they're very fundamental. For any formula, now you have to be careful what you mean by formula of set theory. You have to only write down quantifiers for all there exist, variables, ands, implies, ors, and epsilon, element of, and equal. Those are the only symbols technically you're allowed to use. So take any formula. Well, every formula has a formula of variables. So these will stand for what we call the free variables of the formulas of the formula. That means that there's no quantifier in the formula that bounds, says there exists or for all about those particular variables. So for any formula and any choice out of M1 up to Mn from M, what you want to be thinking of is algebraic closure. So this is an algebra condition. Any formula, think of that like a polynomial equation, and M1 up to Mn are substitutions, are the coefficients of the polynomial, and V0 is the unknown. Now, so we want this property. If that polynomial equation has a solution, if there does exist a V, so that polynomial equation has a solution, now not V1, but M1, so you use M1 up to Mn as your coefficients for your polynomial, so to speak, equation. So if there exists a V, so that this is true, so if there's some choice that makes it true, then there is a choice. So there is an M in M, making it true, with replace V0 by M, and all the others just like they were. Holds, right? So if you can find a witness to the solution to the equation, then there's a witness to the solution to the equation in your model. And that's all in elementary submodel M. Now, we've spent quite a few examples where we try to choose good choices for X alphas and so on. And the interesting thing about elementary submodels and the elementary submodel technique is that we let the elementary submodel choose what we want. And now it's true that you need the axiom of choice, but we're just going to take this. We're not going to prove this, of course. The axiom of choice implies, so here's the very small little piece of set theory and model theory that we're going to want to use, implies every countable set can be expanded, is a subset of countable elementary submodel. Okay, so we'll assume that. Now, with that in hand, we can use these elementary submodels. So we're going to use these, just the philosophy here, use these to choose, to make the good choice. Remember in Hushik's theorem, we chose X alpha and Y alpha, looking at previous coordinates. Use these to choose are a good choice of Y alphas and X alphas, along with a bunch of other things to try to achieve a contradiction to CSD. So I'm going to define we'll take our space X for a space X, and we're trying to analyze X, and we'll just say that, and we're just going to choose an omega 1 sequence, M alpha, alpha element of omega 1, and we'll say that this is an elementary sequence. So we'll do what that axiom of choice theorem says we are able to do, right? So we'll use the full power of set theory that we can. Is an elementary sequence if, right? We put X and his topology implicitly with his topology, and we'll put him in an elementary submodel M0. By the way, the countable elementary submodel will automatically have all the integers in it. It'll automatically have all of the ordinal omega in it. Because it'll keep asking the question, does there exist an integer bigger than 7? Okay, I better have one. Does there exist a first infinite ordinal? Okay, I better have one. Does there exist a first uncountable ordinal? Yes. Okay, I better have one. And not only does it pick one, it picks the actual one. It picks the one. See, we're saying sometimes the confusion is people talk about what is true in M. We're not talking about what's true in M there. We're talking about what is true in the entire. You can't go to the entire universe. That's Gödel's incompleteness theorem, but don't worry about that. So countable elementary submodel, I didn't say that, just simply X is in M0. And secondly, every single member M alpha, each M alpha is a countable. Now, there's no reason other than what we're trying to do to restrict your attention to countable elementary submodels. And thirdly, we'll make it a chain. And thirdly, well, even better than a chain, we'll say that if alpha is less than delta, then we'll look at everything we did all the way up to step alpha. All the choices we made, including every member of every one of those M betas, everything is countable. This is a huge, it's a countable set, and we'll make sure that that countable set is not delta. Actually, being an element of M delta is stronger than being a subset of M delta. And usually in many proofs, at limit ordinal delta, you would let M delta be the union of the choices you made so far. So that's what an elementary sequence is. All right, so don't be intimidated. It's just simply just think of it as, okay, so if we had to choose, well, okay, so just choose, find a solution to every polynomial and add it. And that's all you're doing with choosing a countable elementary submodel. It's just making a good choice for us. And so then we will generalize the idea from Husik's theorem. And so for X, we will always assume that we embed X into 0, 1 to its weight, and call it kappa, so that the weight of X is definable from X. So kappa will be an element of M0. There exists an embedding of X into 0, 1, so there will exist an embedding in M0 by elementarity. Elementarity is very powerful. So X will naturally embed in some Tikhonov power, because we're going to be talking about compact X. And X, for X element of X, let's generalize the notation from Husik. So let's say that X restricted to M alpha is an abbreviates. Okay, so what's happening here is the elementary submodel is choosing many, countably many coordinates out of kappa, but not necessarily in consecutive order. So this abbreviates X to the restriction to the coordinates that M alpha happened to choose. And when that's just simply, all right, so like I said, it's not an initial segment of the coordinates, but it's a perfectly legitimate countable set of coordinates. And the idea is the elementary submodels will choose the important coordinates, right? So it'll make wise choices as to which coordinates should be chosen. And then we'll similarly allow the projection, and we won't bother putting the intersect kappa there. Projection map will be the same thing, right? So it'll be the map from 0, 1 to the kappa, which is probably bigger than omega 1, and onto 0, 1 to the M alpha intersect kappa. And it's just defined as before. little interpretation here. So X, if you take 2 points, X, they may or may not be members of X. Well, let's put them as members of X. If you take 2 points and say that X restricted to M alpha is the same as Y restricted to M alpha, this is the same as saying, technically it means on those coordinates. But of course, the basic open subsets of X can be interpreted as the basic open subsets of the Tikhonov product intersected with X. So if you're one interpretation of saying that X restricted to M alpha is exactly the same as Y restricted to M alpha, is that the open sets is the same as for any U, which M alpha happens to know about, for any basic open U element of M alpha, you can't tell X and Y apart. X is in U if and only if Y is in U. It's the same thing, and it's another interpretation and point of view that can be helpful. So the elementary submodels are picking out those Conley set of coordinates. All right, so that's a tool, and let's see what we can do with this tool. So here's an early result by Juhas using this tool. He didn't actually use elementary submodels, but it's a lot easier if you do. By the way, I wrote a survey paper you might dig up back in, I don't know, 88 or something about using elementary submodels in topology proceedings. So here's a beautiful result of Juhas and Heinel. If every, back to our theme, if every aleph 1 sized subset of X is second countable, has a countable base, then so is X. This is very unexpected. And it doesn't, you might have to assume that X is regular. That's okay. That's what we're assuming that. If every aleph 1 subset of X is second countable, then so is X. Well, before I use our elementary sequence, let me remind you. So remember example 1. Remember that, well, look, if you take an aleph y subset of X and it's second countable, it's certainly separable. So every aleph 1 size subset of X is separable, and we know that means X is separable. So remember that X is separable by this hypothesis. And that means X has a countable dense set. Now you have a countable dense set union any point, and that will be second countable. And so you can just easily deduce, and you need regularity for that. Hence, X is also first countable. Again, why is that? Well, you take your countable dense set, take any point, then you have this dense set, and the character of a point with respect to a dense set is exactly equal to the character of a point with respect to the whole space. That X is separable, which we don't really need except to be able to say that X is first countable. All right, so now let's let M alpha be our elementary sequence. So let M alpha, alpha element of omega 1, be an elementary sequence for X. So he's going to pick out a nice aleph 1 sized subset for us. Okay, so let's give it a name. Let Y equal the union over alpha element omega 1 of X intersect M alpha. Each M alpha picks out a nice countable subset of X for you. Them all up. We might, sometimes we could say that M omega 1 is the union of all the M alphas. It's a theorem of Tarski that M omega 1 is also an elementary submodel. It's not countable anymore, but it's an elementary submodel. So let Y be this. Now, of course, hence, cardinality of Y equals aleph 1. Hence, we can say that Y has countable weight. has a countable base. Let me change colors, just a little variety. All right, so Y has a countable base. He's our witness to this important hypothesis. Now let me point out a little theorem of topology. That means if Y has a countable base, hence every base for Y has a countable subbase. Right? They don't say exactly the same thing. So there is some base for Y that is countable. Now you take any other base for Y, which may not be countable, but because there exists a countable base, you can pick out a countable subset of that base, which is also every base for Y has a countable subbase. Now we want to talk about a base for Y that the models know about. So what we can do is you let B, script B for base, element of M0 be any base for X. All right. And then, because X is first countable, so first countable implies B intersect M alpha, that's a countable subset of B. B intersect M alpha contains a local base in the whole space, a local base for each Y in X intersect M alpha, which is the same as Y intersect M alpha, right? So why is that? Well, because of first countability, right? So this is B is a base for the whole space. So the M alpha knows about little y, and M alpha says, hey, Mr. B, I know that you have a countable subset, which is a local base for Y. There exists a countable subset of B that is a local base for Y. Therefore, M alpha has those countably many, that countable local base is an element of M alpha. And this is even weaker than that. So B intersect M alpha has enough information. It gives you a local base for every member of X intersect M alpha. Well, then, thus, you could call it B omega 1, which is the union of all of those guys. So let's just say it like this: B intersect what I called M omega 1, the union over alpha element of omega 1. M alpha is a base for Y. I'm using the term base a little loosely. Of course, the members of B are open subsets of X, and I just mean they induce a base for Y. You intersect them with Y, and you get a base. Well, in particular, even because, right, it contains a local base for each Y and Y. All right, then. But what did we say about Y? Y has a countable base, is a base. Every base for Y has a countable subbase. So this is a little subtle. So the fact that there is a countable base for Y may mean that that base is completely disjoint from all of the M alphas. And then we wouldn't be able to use knowledge about the M alphas to make any deductions. But by knowing that, in fact, this B omega 1 has a countable base for Y, we can say, and maybe I'll just save a little step, maybe you can fill this in. So there exists a countable subset of B omega 1 that is a base for Y, but every countable subset of B omega 1 is contained in some I'll say, so there exists, I'm skipping a step, there exists a delta less than omega 1, so that B delta intersect M delta has a base, is a base for Y. Now you ask the question. Now we're done. Now, little rigmarole, B delta is an element of M, not M delta, but M delta plus 1. So M delta plus 1 has B as an element. It has M delta as an element. It knows there exists an intersection, so B delta is an element. So B delta is an element of M delta plus 1. So now you ask the question. I don't know why that's appearing here. Now you ask the question, does there exist, here's the question, does there exist a V and X in X such that B delta does not contain a local base at X? That's the question we pose when we look at the definition of elementary submodel, and the answer is no. No. Because, and here it goes backwards, because there is no such X, there is no such M in M delta plus 1, right? B sub delta does have a local base for every member of B X intersect M delta plus 1. Therefore, he has a local base for every point of X. And this finished the proof. So B delta is a base for X. All right. That gives you.
Okay.
Yeah, I'm running out.
Okay. Yeah. No. There are 4 questions from Suprakas Hazra. May I ask him?
Yes. Should I stop sharing to see the questions, or?
Okay. No. Would you like to share? You can share it. Otherwise, I can ask.
Tell me what to do.
Okay, as you wish.
All right. Stop sharing.
Okay. There are 4 questions from Suprakas Hazra. Does every CSD space has some real or complex manifold structure on it? If not, provide me an example, please.
Well, every compact metric space is a CSD space.
Compact metric space.
Yes. So the question is every CSD space, does it have countable weight? But remember that every compact metric space is CSD because it had a G delta diagonal. So the Cantor set is an example of a CSD space that doesn't carry any manifold structure.
Okay, thank you. Next question from Suprakas Hazra. Please let me know if there is some study consists of the homotopy and homology group, the CSD space.
The same answer. I was going to make a joke at the beginning of my talk, given the introduction of what topology was, that I'm going to twist and bend and stretch and break every topological notion you ever thought of, right? So, yeah, these when you're generally even compact metric spaces are very nice spaces, but they don't have necessarily nice homotopy structure, homology structure, anything like that. Because as I said, the best example of saying none of those continua theory type objects exist on the Cantor set. So it all breaks down for the Cantor set.
Okay, third questions from Suprakas Hazra. Every compact metrizably fiber space with a small diagonal is metrizable. My question is, does it have some Riemannian manifold structure on it?
I'm impressed that somebody knew. That was going to be one of my later results, that somebody knew that every compact metrizably fibered space, that's due to Gary Gruenhag, every compact metrizably fibered space is metric. Every CSD is metric, and but no, the class of compact metric spaces and metrizably fibered is too broad to be thinking of anything remotely continuum theoretic on it. Did I forget the question you asked me already?
Okay, one more questions from Suprakash Hazra. Why the small diagonal is called small diagonal? Does it have something to do with geodesics of the space? If such geodesics exist, if we assume, for example, for a Riemannian manifold so.
Yeah, no, the word small wasn't even invented by Hushek. He called it omega-1 inaccessible. And I think it was Eric van Douwen, famous topologist, who just called it small just for a nice name. You know, so it really, but again, no connection to Riemannian manifolds other than SD, because they're all metric if they're compact. But the nature of this investigation is we're looking at very, very strange, typically zero-dimensional spaces, and there's no Riemannian structure on them. So this is set theoretic topology rather than geometric topology or algebraic topology, those sorts of things.
Okay, thanks a lot, sir.
Yeah. How much time is remaining on my clock?
Okay, you can carry on. Okay.
Professor Dow.
Yes.
I am Vishwajit Mitra.
Yes, of course. Hi.
Yeah. One thing I would like to ask you that in the proof of Husek, the elementary model theory, submodel theory, how did you enter into that area? From the problem actually was purely topological. Then from that, how did you get the idea that you need this model theory notion to prove this result?
It goes way back to a talk I gave at the Spring Topology Conference. I was working on a problem, just a generalization of the problem I just presented. The question was, if you have a compact space in which every alpha size subset is metrizable, not second countable, but metrizable, is the space then metrizable? And I was able to solve it, and I ended up, using elementary submodels as the tool to investigate it. So that was the birth for me of seeing the power of elementary submodels, and just became a passion of mine that to advocate to the topological world, more the set theoretic topology world, that this is a very powerful tool. And if you have a powerful tool, why not try to use it to help you when you're investigating hard problems? That's all.
Can you please give me the reference of this model theory? Any reference?
Well, you should look at my survey. It's called Introduction to Applications, Introduction to Elementary Submodels in Topology, I think it's called. But it's in the journal Topology Proceedings in 1988. And I think that's available online now.
Okay, thank you. Now you may carry on.
Okay, proceed.
Could somebody tell me how many more minutes, if any?
Okay, if you wish, you could carry on.
But how many more minutes remain?
Actually, time is over. Still,
time is over.
Okay.
No, okay, yeah, time is over.
Okay, but you can carry on.
Okay.
It's a great opportunity for us to listen. That's why.
Okay, I'll be quick. It's a shame. So I obviously misjudged. As I told you, I realized the talk was too long, so I divided it. Then I divided it again. I did one more. So here's another fact, another reflection result. Example 5 by my numbering. If every separable CSD space.
I think you're not sharing now.
You're right.
Excellent.
You're right. You're right. I forgot to do that. I should be sharing now. Yes.
Right.
If every separable subset of CSDX is metrizable, then so is X. So now I was going to prove that, but I'm out of time, and that proof is similar. It's a lovely proof that uses the elementary sequence. So, you know, like you'd say that you have the elementary sequence M alpha alpha element omega 1, and it's doing its best to pick out a non-separable, bunch of nice separable subspaces, and you could let F alpha equal, that'll be a closed subset, closure in X of X intersect M alpha. And these are all separable. And if you assume they're all metrizable, I can give you the sketch. So somebody interested, maybe it'd be wonderful if you could try to fill in the blanks here. Go back and look at the proof of Huschek's theorem, and we'll take this increasing sequence, F alpha, this is an increasing sequence of compact, separable, metrizable spaces. Remember that the union of an increasing sequence like that is closed because we're in a countably tight space, hence compact. Now we could prove using our elementary sequence and an embedding in 0, 1 to the kappa that this also has weight of F less than or equal aleph 1. That's because it's an increasing union of second countable spaces. Now it's not quite that simple, but close. You can use projection maps and get that the projection onto the coordinates in the union of the M alphas is 1 to 1. And therefore this compact space maps 1 to 1 into a weight aleph 1 space. So it has weight at most O aleph 1. But remember Huschek's theorem says that F has a countable base, right? Because a weight aleph 1 CSD space, and here we're using CSD as closed hereditary, so F has a countable base, and that means F is separable, hence not only that F is separable, hence F is separable, hence, now that's not a big deal, but actually what a big deal is, F equals, if you have a countable dense subset of F, it has to occur in some F delta, and so F has to equal F delta. Where's the contradiction? M delta plus 1 again. M delta plus 1 sees, when you ask the question, are there any other points of X, sees that X actually equals F. There's no other points to choose. Delta plus 1 would have picked them, but he didn't. So since he didn't pick any other points, that's because you've used up all of F. So that's there. I actually not that far from finished. Now a corollary, and this goes back to Huschek, although he had to assume something extra in this corollary. But now we have our first consistency result. The continuum hypothesis implies CSD spaces, in fact, are metrizable. So it's a big open problem, but it's consistently true. right? So the continuum hypothesis says that all CSD spaces are metrizable. The quick proof of that is another way I could have stated this theorem was, if there's a non-metrizable CSD space, one, or maybe, okay, here's a direct proof, right? So if you let X be CSD, every separable, closed separable subset of X has weight at most, because of the continuum hypothesis. If you're separable, you have weight at most. The continuum hypothesis is assumed you have a weight at most L of 1, hence, in fact, weight, hence metrizable. So every separable subspace is metrizable, therefore the whole space is metrizable. Well, let me just say that many other set theoretic axioms and forcing constructions, axioms and forcing constructions, not so many axioms, but forcing models. We build new models of set theory. That's how we prove independence results, Cohen's technique of forcing. So I've had some success in this area. So for example, if you've heard of the proper forcing axiom, it also implies a yes answer. So it implies a yes answer, and there are many, all such results suggest yes, right? It suggests that the answer should be yes. Now, if you allow me, interrupt me if you don't. Somebody just mentioned a couple of results I wanted to say about Gruenhagen. So Gruenhagen in ZFC, that's beautiful in ZFC, as somebody said, compact metrizably fibered. That's a notion due to Kachuk. What metrizably fibered means, CSD spaces are metrizable. Metrizably fibered means you have a continuous map from your space onto a metric space, hence a compact metric space, and every fiber, every preimage of every point is also metric. And the proof is can be done as similar to Huschig's, but anyway, that's that. And he also, so if their space is hereditarily Lindelof. And that's really it. But okay, as I said, I'll just just make a remark. It'll take me 2 more minutes. Okay, so it seems ZFC, ZFC. You say Z in India, don't you? I used to say Z when I was in Canada. It seems ZFC should say yes. And that's what's so beautiful about this problem. You know, many people don't like independence results. Well, this is a question that could well be simply true. And I think one has to admit, it's not a very artificial question. Compact, metrizable, small diagonal, those are very simple to state notions. So it's a very natural question, and we just don't know. But by analogy, I just want to mention an analogy that I also worked on a long time ago. So here's a similar question. So we say that a space X, okay, so I don't need to state the question. Let me try that again. Sorry, I'm trying a little bit rushing. So here's, if X, you have a space X, don't assume it's compact anymore. If X is first countable, and actually you could also generalize that to countably type, but even first countable is an interesting remark. And so here's the Aleph 1 sized reflection property. And every open cover of size Aleph 1 at most aleph 1, has a finite subcover. So assume this about X. This is called initial aleph 1 compactness. The Russian school introduced initial aleph 1 compactness and final compactness. This is called initially omega 1 compact. So if X is first countable and open covers have a finite subcover, then is X actually compact? So it's a similar kind of thing, right? So if, in other words, if X isn't compact, can you know it by just looking at covers of size aleph 1? So I'll just remark that the same set theoretic results, CH, the proper forcing axiom, and many forcings like Cohen forcing, many forcings say yes. All right, so that would say yes. But let's not get complacent. Even Martin's axiom, so MA, which is a weakening of PFA, probably many of you listening have heard of Martin's axiom, MA plus not CH does not say yes. So a very tricky question. But even MA plus not CH does not say yes. So that means that you can produce a model of Martin's axiom holding, PFA failing, and yet there is a first countable space in which every aleph 1 size cover has a finite subcover, but the space isn't compact. Unfortunately, it's difficult to see any connection between these constructions and the CSD constructions. So that was my punchline I wanted to end with. And so thank you very much for listening. I'm sorry I went over time. I hate doing that, but there we go.
Thank you, sir. It's a wonderful lecture. So we enjoyed it so much. So he has given so many concepts. He has introduced so many things which are involved. The results he has shown are very involved results, but he presented so nicely and lucidly. We enjoyed it so much. If there is any other question from the audience, you may ask. Is there any question? If not, then
somebody
thank
just
you,
said
sir.
thank you. Thank you very
Thank you
much.
once again. Yeah.
Yes. Thank you all for listening. I hope. Yeah. So I turn off my mic now, yes?
Okay. Okay.
Okay,
Thank
sir.
you. Okay. Thank you, Professor Dow, for your nice lecture. I also express my sincere
somebody raised the point, and I find it awkward too, that we don't hear any sound. So I thought I would contribute some sound.
Are we still connected?
Yes, we are connected, but I don't know why the organizers. Probably the secretary was here.
Yeah, we can hear you, but not the organizers.
Yes.
So what should we do?
Let's wait for a while.
Hello.
Yes, we
Yes.
can hear.
Oh, can you hear me? Okay. Now let us move to the next session. May I request in this session, our chairperson is a well-known name in the field of category theory and the eminent research in this field, Professor Parthapratim Ghosh, Department of Mathematics and Statistics, University of South Africa. May I request Professor Ghosh to kindly chair this session.
Thank you, Prashanto. I have the pleasure to have been introduced with so kind words. I have also the pleasure to chair this session to be given by Professor Bishwajit Mitra. Bishwajit Mitra did his master's in pure mathematics from Calcutta University, and his doctoral thesis was on pseudo-compact spaces and real compact spaces, their generalizations and interrelations, under Professor S.K. Acharya, I think sometime in 2007. Later on, he attended several conferences, not only in the country, but beyond. He was a postdoctoral fellow also in South Africa with myself, and I had the opportunity to work with him also during this period. He is well known for his work in rings of continuous functions. I now do give the floor to Vishwajit, although it is not more a floor, the webinar. His topic is effect of dense subrings of a commutative ring with identity. So Vishwajit, we await hearing you. Thank you.
Okay, thank you, Parthuda, and for introducing me so nicely. And I also thanks convey my thanks to the organizer, especially the Prashantoda, who has given me an invitation to deliver something. So I am now sharing my screen. I hope everyone can view the board. Is it visible? The board is visible?
Yes, it is.
Yes, sir. Okay, thank you. So the title of my lecture is Effect of Dense Subrings on the spectrums of commutative ring with identity. So before Before beginning my lecture, let me make some initial assumption. By a ring, we always mean it is a commutative ring with identity. And subrings, whenever we talk about subrings, so subrings under discussions always contain the identity of the original ring and third one, by a homomorphism, it always mean it is identity preserving. So these are the three basic assumptions we need before beginning the discussion.
Excuse me, Vishwajit, please can you change your background?
Okay.
To white and your writing to black.
Okay, just a minute. Copy, paste. Is it okay?
I think so, yes.
Okay.
It's fine. It's fine.
So these are the basic three assumptions we'd like to share with all of you. Now let's come to the term spectrum, which is the basic of this lecture. So what is spectrum? So these are the two terms. One is spectrum, another one is maximal spectrum. So let me give some introduction to it. Suppose A is a ring. That means it's a commutative ring with identity. And let PA is the family of all prime ideals of A, and MA is the family of all maximal ideals of A. Clearly, MA is contained in PA. Now, for each A belongs to A, let me introduce XAA is the family of all prime ideals, so that A is not in P. Then it is a routine exercise to check that XAA intersection XBA is nothing but XABA. And that says that this family where A is in A is a base for open sets for some topology on P of A. This topology usually called as Zariski topology. Zariski topology. And PA with this Zariski topology usually called spectrum of A. Now, if you restrict the Zariski topology over MA, restrict the Zariski topology over MA, then MA with that restricted Jarsky topology is called maximal spectrum of A. Fine. Now we have a nice functorial representation here. Suppose A is a ring, I mean commutative ring with identity, and B is also a commutative ring with identity. From A to B, you have a ring homomorphism. Then this will induce a continuous map from spec B to spec A. And that is why spec can be treated as a functor in the language of category, and it is in fact a contravariant functor in the sense it reverses the arrows, contravariant functor. But another part which is given in the exercise of Atia and McDonald books, that if star of spec B is dense in spec A, if and only if kernel of F is contained in nil radical of A, which is nothing but the intersection of all prime ideals of A. So in particular, if F is 1, 1, then kernel F turns out to be the 0 elements. So in that case, F star of spec B is dense in spec A. Now, what about the maximal spectrum? Okay, it is also not very difficult to check that spec A is actually a compact T0 space. But in case of maximal spectrum, we do not have such nice functorial representation, because if A to B, if you have a ring homomorphism, this does not induce a map F star from max B to max A. It doesn't do that. Reason is quite simple, because if you consider a maximal ideal from B, then F star, okay, by the way, I have forgotten to define the F star probably in the last year. The F star is defined as this: F star of P is nothing but the F inverse of P, where P is the prime ideal of B. So if you take the inverse image of P under F, then that again is a prime ideal. So the problem doesn't arise here. But the problem what the problem happens here, that if you consider F star M, if you define that F inverse M, this portion may not be maximal. First problem, may not be maximal. And second problem is this is, since this is a prime ideal, it may have more than one maximal extension. It can be extended to more than one maximal ideals. But the situation can be managed if you think about PM ring. So the situation can be adjusted if you consider the PM ring. PM ring means where every prime ideals can be extended to a unique maximal ideal. So these kind of rings are called PM ring, and in rings of continuous function, CX is the most famous examples of PM ring. So Under this setup, we have this functorial representation. So once you have A to B, a morphism, then this will induce a morphism. I am denoting it by F lowest from max B to max A, which is F star M is the unique maximal ideal containing F inverse A. This is now possible because we are now in the field of PM rings. So this turns out to be functorial, it can be easily checked. However, the problem is not my problem is not in this situation. And maximal spectrum of a commutative ring with 1 is always compact T1 space. It need not be even Hausdorff. So in some sense, it can be said that the spectrums or maximal spectrums are not very good with respect to separation axioms. But within the class of PM rings, in case of PM rings, we have two immediate nice result, that A is PM if and only if spec of A is normal and max of A, that means maximal spectrum of A, is T2. So within the class of PM rings, the spectrum turns out to be normal and maximal spectrum turns out to be Hausdorff. So in case of PM rings, maximal spectrums is compact Hausdorff spaces. This was done by Macro and Orsatti. In the year 1971. So, and further, Schwarz and Tressel they also did different works on PM rings. In the year 2010, they characterized when spectrum of A to be completely normal. So spec of A, they proved that spec of A is completely normal if and only if the following equation holds. So the equation is a bit tricky, however I am writing it down. The equation is for all SA belongs to A, there exists X and X dash belongs to A, and a natural number is there, such that S to the power K minus XSA and S to the power K minus X dash S square minus SA, that turns out to be 0. It's a bit tricky equation. However, an easier description is there, that spec of A is Cn if and only if all prime ideals of A containing a given prime ideals are in chain under set inclusion relation. So this criteria is equivalent to complete normality. However, the above equation tells one fact, that that homomorphic image of a completely normal Okay, a homomorphic image of those rings whose spectrum is completely normal is again completely normal. So for simplicity, let me call A is completely normal or normal if and only if spec A is completely normal or normal respectively. So that's that the way we are saying that A is completely normal or normal if the spectrum is so. So in that language, now we can say that if any completely normal homomorphic image of any completely normal ring is again completely normal because of that in equation. So this part done by Schwarz, and now we come to the motivation of this lecture. So as Parthoda told that I did my PhD in rings of continuous function, so I have some soft emotion over there. So let us denote Cx is the family of all real valued continuous functions, and sister x bounded real valued continuous function. Then it is Cx, both Cx and sister x are commutative ring with ones and under pointwise addition and multiplication, and any subring of Cx containing sister x, we call it intermediate subring. Intermediate subring. The result is that this, okay, maximal spectrum of Cx usually called structure space of Cx, and respectively sister x. If you consider sister x, then it is called structure space of sister x. The main result is that the structure space of Cx and sister x are homeomorphic. And that is homeomorphic to beta x, the Stone-Check compactification of x. And also it is known result that the intermediate subrings of Cx, their structure space are also homeomorphic, and they are also homeomorphic to beta x. Now Macro and Orsalti they have further shown that the spectrum of Cx is embedded in spectrum of sister x, and the way they prove that that involve two steps. The first step is that what they have shown that if P is a prime ideal of Cx, sister x, if P belongs to P of sister x, and you suppose group of units of Cx, if P intersection U is empty, then Pu, which is written as Pu, where P belongs to P and U belongs to U, is a prime ideal of Cx, and Pu intersection sister x is simply P. So this is the first result, and they mapped sister from spec of Cx to spec of sister X, taking P goes to P intersection U, that is spec of sister X, sorry, Cx to spec of sister X. They used a map P goes to P intersection sister X, and they have shown that this is actually a homeomorphism. Homeomorphism into, I mean, it is an embedding. So in this way, they have proved that spec of Cx is embedded in spec of sister X. But this fact, the number one fact we have observed, can be generalized if we take A is a, suppose B is a ring of fraction of A, that means P is equal to some S inverse A, where S is a multiplicative closed subsets of A without 0 and 0 divisor, so on. These are the condition over there. Then any prime ideals, if you take any prime ideals P from spec of A, choose any prime ideal spec of A such that P intersection S is empty, then S inverse P is also a prime ideal, and S inverse P intersection A turns out to be P. Why I am telling this theorem? Because in their paper, Macro and Orsatti said that these results can be generalized if you assume A to be absolutely convex and many other properties which Cx enjoys. So it's a very stronger properties. Without assuming this, if you assume just B is a ring of fraction of A, in fact Cx turns out to be that. If you take S to be U, then Cx turns out to be ring of fraction of sister X. The result still holds. Now our intention, so our motivation is to extend how much we can extend, how much we can extend these type of results to an arbitrary ring. So that's the question, how much we can extend these results to an arbitrary ring. For that, we gave a concept of new notion that is called dense subring. Let me draw the picture. What does it mean? Suppose you have A and B. What do you mean by A is dense in B? What is the meaning of that? It means if you take an ideal, any ideal I, and if you consider its radical, say this is the radical of I, then if you choose any points A which is not in radical of I, then there exists another point B which is still not in radical of I, but their product AB is in A. So that's the description of a dense subring. That means if for any ideal I of AB and for any A not in radical of I, there exists B not in radical of I such that AB is a member of A. Examples are immediate. Number one example is Z is dense in Q, and Q is dense in R, and third one is sister X is dense in Cx. In fact, if B is a ring of fraction of A, then A is dense in B. In fact, sister X and Cx are particular example of the example 4. Now we have some properties of dense subrings. First of all, let me draw the picture. Suppose A, B, C is an intermediate ring. If A is dense in C, C is dense in B, then A is dense in B. So A is dense in C, C is dense in B, so that implies A is dense in B. Second property is that if you have A, B, and suppose you have intermediate subring C, if A is dense in B, then it makes C dense in B. So if A is dense in B, then C is also dense in B. But unfortunately, we don't know the following results. That is, if A, C, B, if A is dense in B, we don't know whether A is dense in C. This part is not known. We don't know this fact. In fact, we did not crack any example that result doesn't hold. So this part is still could not solve it. We could not solve. Anyhow, but another interesting property that we have. First, note that in our case, as A is subring of B, so we immediately have an inclusion map from A to B, which is an identity preserving homomorphism. And since this one is injective, we can say that the I star from spec B to spec A is continuous and dense, and I star of spec B is dense in spec A. So our intention is to crack that macro-Orsatti's result that spec of Cx is embedded in spec of sister X. So we already have some ready-made result that I star is already continuous and I star of spec B is dense in in spec A. So if somehow we can show that I star is open, then it is open and as well as 1-1. Then the result which we are expecting in more general setup, then we can reach that to our goal. So next property says that, property 3 says that if A is dense in B, then I star is 1-1 map. So we further approach to our goal. So remaining to show when I star is open. But before that, another nice property we have that any minimal prime ideal of A can be expressed as Q intersection A, where Q is unique minimal prime ideal of B if A is dense in B. So that is another property which is enjoyed by dense subrings. If A is dense in B, then you can express any minimal prime ideals of A precisely in the form Q intersection A, where Q is the unique minimal prime ideal of B. And finally, as we have already seen that if A is dense in B, then I star is 1-1, and now we can we have reached to our goal by the following property 5, that A is dense in B if and only if I star is 1-1 and open. So previously we were lacking of showing I star to be 1-1. Now we have the result that 1-1 openness of I star and 1-1ness of I star is true when A is dense in B and vice versa. So that is a representation of a dense subring of a B. So let me sketch the proof of this result. So okay, the corollary before going to the sketch. So now we have this corollary that A is dense in B if and only if spec of B is densely embedded in spec of A via I star. So this result generalizes the results of macro-Rorty. They have shown for Cx and C star x, but now we have in more general setup that if A is dense in B and since C star x is dense in Cx, so this result follows from this particular results. So if A is dense in B, then spec if and only spec B is densely embedded in spec A. So now we come to the sketch of that proof. The proof is not so difficult. It's just a slight manipulation. I'm just giving you the sketch. Suppose you are given A is dense in B. This is given to you. By some previous result, we can immediately say that I star is 1-1. So you only have to show that. That is what we need to show, that I star is open. So for that, it is better to show that it takes basic open set to an open set. So take any basic open set in spec B. So please remind that I star is a map from spec B to spec A. So this is the map, and the basic open sets here are looks like X A B where A belongs to B, and the basic open sets are looking here XAA, where A belongs to A. So it is better to show that it carries basic open sets to an open set. So for that, take any basic open set here, XAB. So we need to show that I star of this is open in I star of spec of B. So we have I star of spec B here, and spec is A is here. So this is the image I star of XAB. So if you choose any point here, then we have to show there exists a basic open set containing that point and contained in the I star XB, and that basic open set can be represented by some basic open set here in spec A intersection with this. So for that, so take any point from here. So choose any point, say Q. So Q belongs to I star of XAB. Choose any point from here, and I star of XAB is contained in I star of spec B. So we have two possibility. Q is also member of here. Q is also member of here. So I can express Q as some P intersection A, but that choice of P should not be different because I star is 1 1. As A is dense in B, we already have this setup. So I star is 1 1. So since Q is here and also Q is here, so choice of P in general may be different, but as I star is 1 1, the choice of P should be unique. So now I can say that Q should be written as P intersection A, where P belongs to XAB. So this conclusion we can make because I star is 1 1. So this says that A is not a member of P. So A is not a member of P. So that means now for prime ideal, P and radical P are same. So as A is dense in B, given that A is dense in B, so there exists some P not in radical of P. That means P says that AB belongs to A. So now remaining task is that Q belongs to XAB A intersection I star of spec B, and that is subset of X, B, B, and his I star image. So only remaining to show that this XABA turns out to be the required basic open set in A, in spec A, such that whose restriction over I star spec B is contained in this. And from there we can conclude that this is a open set in I star of spec B. Conversely, suppose now I star is open and 1 1, then you have to show that A is dense in B. So for that, A you take B. So now you choose an ideal I. So this should be the radical of I. Now suppose A is not in radical of I. Radical of I. That means A is not member of a prime ideal containing I or some prime ideal P containing I, then so P belongs to, I can say that P belongs to X AB. As I star is open, so I star P belongs to I star of XAB. Now that turns out to be open in I star of spec B. As this is open, so it should contain some XBA intersection I star of spec B, or some B belongs to B. Then with little manipulation, it can be proved that in this setup, A will be a member of radical of ideal generated by B. This can be proved. If the situation is like that, then A can be generated, is a member of radical of ideal generated by B. So that means some power of n must be member of B, and so A to the power n should be written as some u times B. And this can be checked that u is also not a member of radical of I, and as A is a member of A because yes, as sorry, I just wrote it invertedly. It should be B is a member of A, so B to the power n is a member of ideal generated by A, so B to the power n should be written as UA. And as B is a member of A, so B to the power n should be member of A, and it can be shown that U is not a member of radical I. So finally we have seen that there exists another member U, which is not a member of radical I, but their product is a member of A. So that this is the proof of this result. Once you have this result, then using this result, you can we can prove that if A is completely normal ring and A is dense in B, then it will follow that B is also completely normal, and hence B is normal. That is, B is PM. So just complete normality of the ring A, and if it is dense in B, will make B also completely normal, and hence normal, and B turns out to be PM. And then from this theorem, we can easily prove that if A is completely normal and dense subring of B, then maximal spectrum of A is homeomorphic with maximal spectrum of B. Now this is the more general result that we are expecting. In case of CX is sister X is a completely normal subring, because there you can have if you have any prime ideals, then all the prime ideals containing the given prime ideals are in the chain form. So sister X is a completely normal, and sister X is dense in CX because it is a ring of fraction of CX is a ring of fraction of sister X. This results of CX now follows as a corollary from the more general result that if A is completely normal and dense subring of B, then their maximal spectrums are homeomorphic. And what about the intermediate subrings? For intermediate subrings, as I told earlier, that if A is a ring, A is a subring of B, and suppose C is an intermediate ring. If A is dense in B, then we don't know whether A is dense in C. We don't know. So if we assume this, that any two intermediate subring of B are homeomorphic, the maximal spectrum will be homeomorphic if A is dense in that intermediate subring. If we assume this condition, then the result follows that if A is dense in the intermediate subring B, sorry, C and D, say suppose, then maximal spectrum of C is homeomorphic with maximal. Of course, A should be completely normal. A is completely normal and dense in the intermediate subring of C and D, then maximal spectrum of C and maximal spectrum of D, they are homeomorphic, and that is homeomorphic with maximal spectrum of A. So in case of CX and sister X, what happens that any intermediate subring of CX, if you take any intermediate subring of CX, then sister X is dense in that intermediate subring. So it naturally happens in case of CX and sister X, but more generally, we don't know whether this result is true. So in that case, we have to assume for time being that A is dense in those intermediate subrings, then those intermediate subrings, their maximal spectrum turns out to be homeomorphic. And now this is the whole of now I can now stop here because I still have some problems in mind regarding the nature of the compact spaces. How does it look, and that there's the maximal spectrum. If A is a PM ring, then how the maximal spectrums of those rings behaves, and whether we can have some kind of that maximal spectrum, is it a compactification of some well-known space or not, or not well-known, if it is a compactification of some space or not. So this type of the problems we are looking for. Anyhow, now that is the end of my topic. Hello.
Thank you, Vishwajit, for your nice talk. From the audience, is there any question? From the audience, is there any question?
Can you provide some references for these?
Sure.
Hi, Vishwajit. Alan Dow here. What are some of your sources of examples besides C star of X and C of X, where you get other interesting rings from?
Other interesting, sorry?
When you're exploring questions, it's good to have examples to see what works and what doesn't work. And besides C of X, where do you find your examples?
Truly speaking, honestly speaking, other than CX, I did not find any kind of good examples to be discussed, but I believe there are many examples, and I shall look for those. If actually, as I told earlier, I gave some examples which are very preliminary. Even I don't know whether Z is dense in Zi. So this example I was looking for, whether Z is dense in Zi. So at present, other than CX, I don't have any good example. I'm sorry for that, but
no, that's okay. I just wondered. And also for intermediate rings between C star of X and C of X, do they have, I believe, but I'm not 100% sure, they have topological interpretations as by looking at the subsets of beta X that contain X, their connection there?
No, for general ring.
Intermediate ring.
For intermediate ring, that is homeomorphic to beta X.
When you take an intermediate ring, does it arise by, can such examples arise by looking at subsets of beta X that are intermediate between X and beta X? like all functions that extend continuously. Okay, if not, all right.
Oh, that means you are asking that if you consider, if I take any intermediate subrings of Cx, then can it be represented as
The
which
set of
are
all continuous functions on a subset, or some analogous,
which have an
like
extension up to
sure. Yes.
yes, that type of work I think is there. I cannot give at present the proper reference, but I have seen this kind of works probably by Planck in his paper.
Yes, I think there's a work by Planck which says that each intermediate ring can be associated with the
And they call it epsilon AX, something like that.
Yes, epsilon AX, yes.
Yeah.
There is a work by Planck in the year probably 1978.
Well, I confess my ring theory is so weak. I try to translate things to topology to try to understand it better.
Yeah. No, I am also not very good in algebra, but okay, I'm trying to generalize those results in Cx and C star x to an arbitrary commutative ring so that how much
Sure.
you can extend it.
Absolutely, that's what we do. Yep.
So this is
Okay.
Yes.
Okay, Vishwajit, I'm Prashant Sena. We have some problems in chat box from Kishore Chetri. Is the concept of dense subring similar to the notion of dense subsets of metric space?
No. They are different. I have given the name because I am quite fascinating over topology. And also there is a reason for denseness because somehow you can bring down some elements by taking products and with other elements to the elements of A. So in this way, it is just name. I don't think that it should have any relation with the denseness of a topological spaces. No, this is not such a relation.
Okay.
But somehow we have a relation. If you can forcibly argue with me, then I can say, okay, A is dense in B, then spectrum of B is dense in spectrum of A. That latter part of denseness is topological. So in that connection, okay, you have some kind of similarity, but I do not agree that.
Okay, one more question, a similar type of question from Sadiqur Rahman. Does there is the concept of separable subring?
Separable subrings? No. Actually, people are getting confusing with the term denseness. So, okay, you can do. I am trying to do some kind of similarity, but I have not said over here. But I don't expect that you do the same kind of topological treatment over here. You may give some another interpretation of separability. You may have, but not like the topological separability. So these parts you can do. You can say, for example, if you take a ring, if you take a subring, if you consider its closure. Closure means you are taking all those points such that there exists some another points whose product is in A. If you take in this way, then I just initially check that this closeness condition satisfies some properties which is similar to the topological closeness, but that is useless for me in my opinion. So you may search for dense subring, which kind of properties they share algebraically. If you have it, for example, in case of minimal prime ideas. So we got a nice description of minimal prime ideas when you have dense subring, because you can express that minimal prime ideas by some unique minimal prime ideas in B with intersection with A. So this automatically gives you an idea that somehow you can talk about the structure space with minimal prime ideals, not structure space. If you consider if you give the Zariski topology on the minimal prime ideals over A and minimal prime ideals over B, there is a nice correspondence if A is dense in B. So you can search for those kind of results. So what will happen if A is dense in B? So if you give the Zariski topology and minimal prime ideals of A, then that minimal prime ideal, you can uniquely associate the minimal prime ideals of B because of that particular results. Then how does it relate it? How does it relate this to topological space? You can discuss this kind of results in future also.
Okay, one more question from Payal Kormakar. Can you give us some example of PM ring?
Yes, CX is one of the great example that Professor Dow told me. Is there any other examples? Other examples
Okay,
except
actually, you have described it.
Yes.
Okay. Okay. One more question from Payal Kormakar. Although it is known, how can we define a homomorphism between the structure space of CX and sister X? Does it depend on the set X?
Yes, depend on set X means yes, structure space is nothing but the maximal spectrum of CX and sister X, and it can be shown that this is precisely the compactification of X. That's nothing but Stonecheck compactification of X. So definitely it is related with X. So here also I am trying to maybe Professor Dow may help me that I am trying to find out. Suppose you have a two subring, A is dense in B, then what will happen that the maximal spectrum of A, that is a compact Hausdorff space, because we are talking about PM ring. So this compact Hausdorff space, is it a compactification of some space? Can I associate the space X some way? We can search for X. So I have some plan in my mind that I consider X to be all those maximal ideal whose intersection with A is again a maximal ideal. Actually, I am trying to correlate with the facts in CX. Actually, in CX, the situation happens if and only if M is a real maximal ideal. So I am trying to trying to associate that if A is dense in B, now if we are looking for all those maximal ideals whose traces over A is again a maximal ideal, pick out those collection, take out this collection, then consider it as a X. Is it if X is compactification is that particular that maximal spectrum of A? So these kind of problems still are in my mind, so I shall go for it.
Okay, one more question. Is it possible to characterize minimal dense subring of a ring, in particular for CX?
It may be a good question. I have not thought about it, but okay, I shall think whether it can be characterized, because dense subring is completely new. We have introduced this concept, and we have many things to do further. How does it related? How does it affect the algebra of algebraic properties of the rings? So this needs more work, but I think that we can do that. We can work on that question, that whether minimal dense subring like that.
Okay, does there exist does there the existence theorem of maximal spectrum?
Yes, because once you are considering axiom of choice, you have a existence of maximal ideals, so definitely you can go for maximal spectrum. Once you have the existence of maximal ideals, then you can talk about its maximal spectrum, no problem. But you have to assume axiom of choice for that.
Okay, question came from Sadikur Rahman, that earlier question. Okay.
Okay. Oh, Pathoshidi told me to give.
Okay. One more. That is some advice for some good books on topology, or related to your work.
For me, Angel King is the only good book for me for topology.
Angel King.
Angel King. That is the only book. I mean, for me, it is a very good book. Angel King. You can go for that. And Othushidi asked for some references. Can I give you the reference later, because I have not written it down. And
Okay, no problem.
I did not prepare any slide.
Vishwajit, did you try the point-free rings of continuous functions?
No, that is in my mind.
Yeah, I think I have heard Themba speaking around something like this also. But point-free rings could be also a very interesting place for investigation.
Mm-hmm. I now, what I say that I'm now reading those rings, so probably I can have some results regarding point-free rings. I may let you know.
Okay. If there are any other questions from the audience? Are there any other questions from the audience? If not, let's thank the speaker again. Thank you for your nice talk.
Thank
I
you.
hand over to the convener.
Okay. Possibly I was muted at the end of the first session. I express my sincere thanks to Dr. Debra and Professor Dow for his lucid and informative lectures. And I think our students and research scholars will be highly benefited for his lecture. For Bishwajit, I also express my thanks to Parthapratim Ghosh, chairperson, and Bishwajit Mitro. This lecture was also nice, lucid, and wonderful. It was also very informative. Okay, thanks a lot to all of you.
Okay, thank you.
Okay. Okay, Dow.
You are muted, Professor Dow.
Okay. Professor Dow, I think you are muted.
Yes.
So I fixed that. Yes, thank you. I just said thank you very much and good evening to everybody. My day is just starting, but
And George, good morning to you. Is it possible for you to attend tomorrow?
yes, I've rearranged. I'll start my other meeting a little later.
Thank you.
Yes.
Okay, thanks. Thanks a lot. Okay.
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 Bye.
Bye.
Okay, bye. So we'll meet tomorrow once again. Okay. So bye to all.
Bye.
Bye. So we are leaving.
Okay.
Bye to all. Thanks.
Later on.
Mm-hmm.
Just you leave later on. If you are, if it is possible for you to stay here, please stay.
Okay.
Bishoj, Partho, whether Partho has?
He has left.
Oh, he has left. Atish is there. Okay. Okay, all the participants said goodbye. Okay, we are going to complete the program. Okay, actually, just we are waiting for our faculty members and speakers and chairperson. If it is possible for you to stay back, otherwise other participants may leave.
Sir, should I stop streaming on YouTube?
Okay, no need. Later on. Just
okay.
আমরা বাংলা একটু কথা বলতে পারি নাকি? অতসী কালকে আসছো তো?
হ্যাঁ আছি।
আচ্ছা ঠিক আছে। বিশ্বজিৎ লেকচারটা খুবই ভালো হয়েছে,
হ্যাঁ বিশ্বজিৎ খুব ভালো বলেছো।
খুব ভালো বলেছে, খুব ভালো বলেছে।
বোঝা গেছে?
হ্যাঁ বোঝা
একদম
গেছে,
দারুণ,
দারুণ বোঝা গেছে। আমি এই
ঝরঝরে
জন্যই-
একেবারে।
হ্যাঁ হ্যাঁ। এবং তুমি যে ওটা প্রেজেন্ট করেছো না, প্রেজেন্ট করার জন্য খুবই সুবিধা হয়েছে। এটা আগের লেকচারের যেটা অসুবিধা, আমি তোমাকে একটা মেসেজ করেছিলাম বিশ্বজিৎ, অ্যালান্ডাওকে কি বলবো, উনি ট্রায়াল মিটিং কিন্তু করছিলেন, স্ক্রিন শেয়ার করছিলেন, সেটা করলে একটু ভালো হতো। তোমার লেকচারটা অসাধারণ হয়েছে, অ্যালান্ডাও একটা অসাধারণ আছে।
অ্যালান্ডারটা অনেক ডিপ না ব্যাপারটা?
হ্যাঁ অনেক deep, অনেক deep।
আমারটা অনেক লুজ, কিন্তু অ্যালান্ডারটা
না,
অনেক
lose না হলেও তুমিও বেশ ভালো জায়গাতেই গেছো, কাজটা ভালো জায়গাতে। পার্থ তো চলে গেছে। আচ্ছা, আমি আমাদের ডিপার্টমেন্টের ছাত্র ছাত্রী এবং এদের কিছু স্ক্রিনশট নিয়েছো তোমরা? হ্যালো কল্লোল।
স্যার আমি স্ট্রিমিং
না, আমাদের হুমায়ুন বা আরো যাদের বলা হয়েছিল স্ক্রিনশট নিয়েছো?
আশা করি নিয়েছো ওরা।
আচ্ছা আচ্ছা, যদি এটা রেকর্ড হয়ে যাচ্ছে। বিশ্বজিৎ, আমি একটা রিকোয়েস্ট করছি অ্যালান্ডাওকে, আমি যখন বলেছি তখন মিউটেড ছিলাম, একটা ফুল রাইট আপ দেওয়া যাবে? আমরা একটা প্রসিডিংস বার করবো ভাবছি।
হ্যাঁ দেওয়া যাবে।
আচ্ছা ঠিক আছে, কালকে আমি অবশ্য অ্যালান্ডাওকে আমি মেল করবো, একটা রাইট আপ দিলে তাহলে সুবিধা হয় আর কি। আমি এটা ওই কথাটা যখন বলছিলাম তখন মিউটেড ছিলাম, আমি বলতে ভুলে গেলাম।
আচ্ছা আচ্ছা,
আমি ওনাকে মেল করে দেবো।
মেল করে দিও।
হ্যাঁ
কল্লোল, পার্টিসিপেন্ট মানে ডিপার্টমেন্টে ছাড়া আর যারা আছে তুমি করতে পারবে, ওরা আমি 5-6 জনকে করে দিয়েছি।
হ্যাঁ আমি বিশ্বজিৎ অত পার্থ বেরিয়ে যাবে আমি বুঝতে পারিনি।
আমি রিমুভ করে দিয়েছি।
আচ্ছা,
আমি রিমুভ করে দিয়েছি, যারা বাইরে ছিল তাদের রিমুভ করে দিয়েছি।
আচ্ছা, অতসী কিছু বলো।
কি বলবো?
যা খুশি বল আমার ছাত্রছাত্রীদের উদ্দেশ্যে।
যা খুশি আবার কি?
যা খুশি মানে রেলেভেন্ট টু দা,
মানে কি?
বিশ্বজিৎ, আমি সাগর বলছি।
হ্যাঁ ওই প্রশ্নটা সাগরেরই ছিল সম্ভবত।
হ্যাঁ হ্যাঁ হ্যাঁ, ওই মিনিমাল কোশ্চেনটা আমার ছিল, কারণ ওই কি বলে যেন, ওই এর কাজ আছে, কি বলে ওয়াটসন স্যারের, যে সিএক্স ছাড়া তার নিচের রিং এরও ম্যাক্সিমাল আইডিয়াল স্পেসটা বিটা এক্স হতে পারে আর কি, ওই রিলেটেড জিজ্ঞাসা করলাম আর কি। হ্যাঁ, ওই লোকালি বাউন্ডেড ইনভার্সন এরকম একটা কন্ডিশন আছে আর কি, সেই জন্য আমি ওই কোশ্চেনটা জিজ্ঞাসা করলাম আর কি, যে মিনিমাম ওইরকম ডেন্স সাবরিং পাওয়া যেতে পারে কিনা।
যাবেই, সেটা নিয়ে ভাবিনি আমি, পাওয়া যাবে।
হ্যাঁ
ঠিক আছে,
একটু ভেবে উত্তর দেবো আমি, ঠিক আছে?
আচ্ছা আচ্ছা, না আমার জাস্ট আর কি, জাস্ট
হ্যাঁ মিনিমাল পাওয়া যাবে।
আমি এখন একটু ওই সাপোর্ট নিয়ে একটা কাজ করছি, ওই সিউডো কম্প্যাক্ট সাপোর্ট যেরকম আছে ওইরকম একটা আপনারও একটা কাজ আছে, ওই হার্ট সাপোর্ট, ওই রিলেটেড একটা নতুন একটা নোশন পেয়েছি, যে সিকেএক্স আর সিসাইএক্স এর মাঝখানে একটা আইডিয়াল একটা সাপোর্ট নিয়ে আর কি, ওইটা নিয়ে এখন কাজ করছি আর কি। আপনার পেপার গুলো দেখছি এখন।
ঠিক আছে প্রশান্ত দাদা, বেরিয়ে যাই তাহলে।
হ্যাঁ ঠিক আছে,
ঠিক আছে,
ওকে ওকে, তাহলে মিটিং শেষ করছি আমরা, তাহলে কালকে আবার দেখা হবে।
আপনি তো থাকুন, আপনি কল্লোলের একটু থাকুন।
আচ্ছা আচ্ছা আচ্ছা, আমি রয়েছি। হ্যাঁ বলো।
আচ্ছা স্যার, বলছি যে লাইভ স্ট্রিমিংটা যেটা কল্লোল করছে না, সেটা যদি মানে আমাদের কলেজের অ্যাকাউন্টটা দিয়ে না করে ওর নিজের অ্যাকাউন্টটা দিয়ে করে ভালো হয় তাহলে, কারণ যখনই পার্টিসিপেন্ট কেউ আসছে সেটা স্ক্রিনে চলে যাচ্ছে নোটিফিকেশন, ওইটা কল্লোলের অ্যাকাউন্টে করলে আর সেটা আসবে না।
তাহলে দেখো, সেটা এই ব্যাপারটা আমি ভালো বুঝি না।
লিংক পাঠানো হয়ে গেছে অলরেডি, এখন হবে না ওরকম করে।
না শোনো, আমি
কিন্তু অনেকে কিন্তু কমেন্ট বক্সে লিখেছে স্যার এটা।
না না সেটা ঠিক আছে,
আমি স্ট্রিমটা বন্ধ করি।
হ্যাঁ
স্ট্রিমিংটা
আমায় বলছো?
আচ্ছা স্ট্রিমিংটা বন্ধ করে দিই।
হ্যাঁ স্ট্রিমিং বন্ধ করো। আচ্ছা শোনো,
হ্যাঁ 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 স্ট্রিমিংটা বন্ধ করে
এর
দাও।
পরের দিন আমাদের তুমি কি বলে স্ক্রিনশট যেন নেয়, ওটা দেখবে কালকে।
হ্যাঁ স্ক্রিনশট নিয়েছি, স্ক্রিনশট নিয়েছি আমি নিয়েছি।
না আমি আরেকটা বলছি, যখন দেখছো যে কেউ বারবার অ্যাডমিট করার জন্য রিকোয়েস্ট করছে, করে দেবে, নাহলে ওটা বড় ডিস্টার্বিং। মানে বারবার ব্লিঙ্ক করছে, স্পিকার করছে।
খুব একটা কাউকে
আমি
দিনে করিনি।
দেখছিলাম, আমি কয়েকজনকে আমি অ্যাডমিট করলাম।
ও তখন হয়তো স্যার কোনো নেটে ইস্যু করছিল হয়তো।
আমি কয়েকজনকে অ্যাডমিট করলাম। যখন আমি প্রথমে বলেছিলাম যে মানে ডিসকাশন শুরু হয়ে যাওয়ার পর অ্যাডমিট করার দরকার নেই, কিন্তু একের পর এক দেখছি আসছে এবং ডিস্টার্বিং।
স্যার ওটুকু
হ্যাঁ স্যার আমি
থাকবে মনে হয়।
হাজারটাকে অ্যাডমিট করেছি।
না আমি তারপরেও করেছি, আমি পরেও করেছি। আমি দেখলাম নাহলে তারা করেই যাচ্ছে অ্যাপ্লাই, আস্ক টু জয়েন।
আচ্ছা স্যার আপনার রেকর্ডিংটা অফ করে দিন।
রেকর্ডিংটা অফ, রাইট, দাঁড়াও।
তাহলে স্যার একটা জিনিস কালকে করতে পারেন, আরো বেশি জনকে এই মিটে আনতে পারেন।
হ্যাঁ গুগল মিটে, রাইট। ওই ছেলেটিকে নিয়ে আসবে।